So I wanted to show you the list of rules basically summarized from the book and a couple of quick examples, and then I'll show you like certain oxidation number rules, and then we're really going to learn this just by practicing, okay? So oxidation numbers or oxidation states, right, are calculated to represent electrons lost or gained by the element when, and then it says forming a compound, but when they undergo a chemical reaction, okay? So free elements, that is elements that aren't part of like chemical compounds, are always oxidation state 0 or oxidation number 0. Monatomic ions, as we talked about, have oxidation numbers equal to their charge. So for iron 3 plus, for example, this would be 3 plus, and for O2 minus, it would just be 2 minus. Now, in a compound or a polyatomic ion, right, the sum of the oxidation numbers are the charge of that substance. So for compounds, that charge is 0, but for polyatomic ions, it's whatever the charge of the ion is. So I'm going to write it like this. The sum of the oxidation numbers is equal to the overall charge. So that means for compounds that overall charge is 0, but for polyatomic ions, the charge is whatever the charge is of that polyatomic ion. Now there are some rules, and it gets a little bit confusing. I try to simplify it a little bit. Essentially, these are the rules from the book, but fluorine is always -1. Oxygen is always -2 unless it's with fluorine or unless it's with another oxygen. Now, halogens are always -1 unless they're with fluorine or oxygen. So basically the hierarchy is this: FOH. Fluorine always gets to be -1. Oxygen is always -1 unless it's, or -2 unless it's with the fluorine or another oxygen. And then all the halogens are all -1 unless they're with oxygen or unless they're with the fluorine. So fluorine gets to be -1 all the time, okay? Hydrogen generally gets to be +1. Oxygen is -2, and group 7 is -1 except for the exception. Group 7 is the halogens, except for the exceptions of when something's bound to a fluorine or an oxygen. Group 6 is generally -2, and group 5 is generally -3. Okay, so those are the rules that we're going to use. Now, if you're thinking to yourself, that might sound a little familiar, that's because those are the numbers that you would get from the periodic table. For example, fluorine and all the halogens, generally speaking, are -1. Right? Because they're 1 away from the noble gas. Oxygen is always -2, except when it's with fluorine. These rules that you're seeing here actually has to do with that top row of the periodic table. Fluorine's a -1, oxygen's a -2 unless it's with fluorine. Nitrogen's a -3 unless it's with the oxygen or fluorine. And carbon is -4 unless it's with oxygen, nitrogen, or fluorine. So it's that top row of the periodic table that we're looking at. Okay, so having said that, let's go ahead and try to calculate some oxidation states. So this is what I'm going to do. For whatever element I'm trying to find the oxidation number for, I'm just going to replace that element with X in an equation. So for example, I want to know the oxidation state of sulfur in this compound here, in SO3, okay? So in order to do that, I'm going to say X plus, and then I'm going to put the charge contributed by these oxygens. It's 3 times -2. Now, what is the charge on SO3, right? The charge on SO3 is 0. It's a compound. So that means, well, I should say 3. I'll use a dot instead of it looks like an X when I draw times. So that's going to be X minus 6 equals 0. So X has to be 6. So that's the oxidation state of the sulfur. Let's do another one. We did a calculation of the oxidation of sulfur in SO3 2 minus now, right? And the way this will change is I'm going to say X, which is the sulfur, plus 3 times minus 2 equals, instead of 0 now because it's an ion, equals minus 2. So again, same equation, X minus 6 equals minus 2, and then you can figure out that is plus 4. So this one's plus 4. If you have, for example, in OF2, this is one of those rules now, fluorine gets to be minus 1, right? So oxygen's charge, we'll call it X, plus 2 times minus 1 equals 0, because it's a compound. So X minus 2 equals 0, so the charge of oxygen must be plus 2, like that. We'll do a couple more examples. So now we have S2O3 thiosulfate, and we want to calculate the charge of the sulfur in thiosulfate. So we have 2X, because I have 2 sulfurs in the compound, plus, again, 3 times minus 2 equals minus 2. So this is going to be 2X minus 6 equals minus 2. Now, it's the same situation we had before, but now we have 2x, right? So it turns out, right, in order for this equation to work, that 2x is equal to 4, and so x is equal to 2. So in thiosulfate, the oxidation number for sulfur is plus 2. Persulfate, S2O8 2 minus. To calculate the oxidation number of the sulfur, we would do exactly the same thing. We would say 2 times X plus 4 times minus 2 equals minus 2. And so I end up getting, gosh, every time I touch the screen, it's moving. It's not supposed to do that. So every time I end up with 2X minus 8 equals minus 2. So that means 2. Wait, must have some static on me or something. 2x is equal to 6, or x is equal to 3, like that. And so the oxidation of sulfur is plus 3. Okay, so as crazy as those rules might seem, if you can remember oxygen's minus 2, and unless it's with fluorine, then you're actually in pretty good shape. I think I want to do one more. I thought of that's an important one to know, is H2O2. Okay, so we assume that hydrogen is plus 1. That's one of the rules. So we're going to say hydrogen, and we want to know the oxidation number of oxygen now. And so we're going to say this. We're going to say 2 times plus 1, that's for the hydrogen, plus 2x equals 0. And then when I do my calculation, I'm going to have 2 plus 2x equals 0, which means x has to be minus 1. So this is one of those instances where oxygen doesn't get to be minus 2. When it's bound to another oxygen, it becomes minus 1. So just a couple more applications now of oxidation numbers. It's often important to figure out which substance is being oxidized and which substance is being reduced. And you do that by identifying the oxidation numbers of elements in a reaction. So, for example, I have this redox reaction. It's the formation of rust. It's a type of combustion reaction. So what's being oxidized and what's being reduced? So iron has an oxidation state of 0 here, because it's a pure element, and O2 as a pure element has an oxidation number of 0. Now, the iron in Fe2O3, if we use our charge balancing rules that we use from doing the compound, this is made of Fe, actually I'll write it down below, Fe, Fe, that's 2E, I don't know what happened there, Fe 3 plus, and I also have O2 minus. That's one of those rules that oxygen gets to be -2 in these ionic compounds. So, having said that, what happened? Well, the iron went from Fe0 to Fe3 plus, and since the oxidation number went up, right, it lost electrons. So each iron lost 3 electrons, right? So iron is being oxidized. Now, if you look at the oxygen, on the left side it's O2 that has 0, and then it goes to become O2 minus. Now the way it does that, and I'm going to balance this just because I don't like it if it's not balanced. I have 2 oxygens on the left, I have 2 oxygens on the right. I had to add 4 electrons total for this to happen, because this is a -4 here, right? So since oxygen is gaining electrons is reduction, oxygen is being reduced. And it's always the case that when, right, you have something being oxidized in a reaction, you have to have something that's being reduced. Now, you'll notice that there's 4 irons in this reaction. So if I wanted to, I could multiply this by 4, multiply that by 4, and then if I multiply that by 4, I get 12, right? How many O2s are involved in the reaction, right? There's 3 of them. So in order to make this work, I actually have to have 3 times that, and then 3 times this would be 6 O2 minuses, right? And then this becomes 12 electrons like this. Now you notice that in this reaction, since it was already balanced, the electrons given up by the iron are exactly the same as the number as the electrons gained by the oxygens in this reaction. So while iron is being oxidized and giving up its electrons, it's actually what has done the reducing of the oxygen. It is the source of the electrons. So we often say while iron is being oxidized, it is the reducing agent for the oxygen. So while iron is being oxidized, it is the reducing agent for oxygen. So iron gets oxidized is the source of the electrons. So that's why we say it's the reducing agent. Now, but we can also say this the other way, being equitable in this kind of thing, right? While oxygen is being reduced, it's actually oxidized. It's the oxidizing agent for iron. So the iron, whatever is being oxidized, is always the reducing agent. It's the thing that provides the electrons. And the thing that's being reduced is always the oxidizing agent. And so these terms can be a little bit confusing, but just remember, figure out what's being oxidized, and that's the reducing agent, and figure out what's being reduced, and that's the oxidizing agent, okay? And you'll notice in this particular problem, oxygen is the oxidizing agent because oxygen is involved in lots of these reactions as an oxidizing agent. And oxidation originally the terminology came from reactions of oxygen and the number of oxygens that were incorporated. Okay, so what we're going to do is we'll do one more example of identifying the oxidizing, what's being oxidized, what's being reduced, and then we'll identify oxidizing agent and reducing agent. And we're just going to look at the oxidation numbers of the elements in the compound. So pretty straightforward for this one. Oxygen is 0 here, but in all these compounds, it's -2. Because it's only 0 when it's combined with itself in the element, and when it's with anything else except fluorine, it's -2. So oxygen is being reduced. So since it's being reduced, it's the oxidizing agent. We can pretty much guess that this then is being oxidized into form CO2. But what we're going to do is we're going to go ahead and calculate the oxidation numbers for octane, that's the C8H10, and for carbon dioxide. So we can show that the oxidation numbers are in fact going up. Okay, so I have I have C8H18, and this is overall charge 0 because it's a compound. So I have 8x plus 18 times 1 plus 1 for the hydrogen is equal to 0. And what I get is that x is equal to 18 over 8, right? So that's equal to 2 1/4, like that. Now, and I know that looks kind of weird. Sorry, -2 1/4, because I have to bring it over to the other side. That's the oxidation state. And really what's happening is elements in a compound, even though they're all carbons, can have slightly different oxidation states. And so they end up having fractional oxidation states when you sort of group them all together. Now, for the carbon and carbon dioxide, so that's what the oxidation state on average is for those carbons. In carbon dioxide, it's just CO2. So this is 0, or sorry, x, and it's going to be plus 2 times -2 for the charge of oxygen, and that's equal to 0, so x equals to +4, like that. So this oxidation state is +4. So in general, what happened is the oxidation state went from being a negative value of 2 1/4 to a positive value. So remember, anytime the oxidation number goes up, it's being oxidized. So carbon is being oxidized in this reaction. So having said that, because it's being oxidized, it's the reducing agent. It's the source of the electrons for the oxygen.